Hi, I'm Ted Kalbfleisch. I'm the founder of Invictus Informatics, and I'm here to talk to you today about data that I've generated for CTLR animals and what we've been able to do with it and what I hope we can do going forward. Okay, so what genetic tests are available? And we've run both of these for CTLR animals now. The first of them is something called whole genome sequencing. That costs $600 and it produces what we call 20-fold coverage. It generates the most comprehensive data set that can be produced. It's completely unbiased by anything other than the reference genome to which you map it. And that's not a huge deal. But it produces some 7 to 8 million variants per animal that are incredibly information rich, with which we can do a great deal. But that $600 price tag is a lot. And what we did with a phase one USDA SBIR grant was demonstrate that in many ways, the much less expensive skim sequencing test or low pass sequencing at a cost of $75 can produce data that will do nearly everything that you all need to do. My other job is as an academic. I do much of what I do is horse genetics. Just to aside, if you hear me say foal instead of calf, please, I beg your indulgence. What I would love is that everybody just generated the 20x data. The reality is that is just too steep a price tag. And as I'll describe later, for most things that you all will need going forward, that $75 test will be just fine. The price on sequencing has fallen precipitously over the last 20 years. 20 years ago, to generate that data set would have cost about $2.3 billion. Yeah, we're down to 600 now. Pretty decent drive towards zero. But the reality is that low pass sequencing test is almost always going to be about 10-fold less expensive than the whole genome sequencing. So even if we get to $60 for 20-fold coverage, I'm certain that the cattle industry as a whole would be much happier paying $6 a head than 60. So this is a data set that I believe will exist forever. That is, I believe the companies are going to be generating it forever. So let's figure out how to use it as well as we can. Okay, so what do these data look like? So in this middle panel here is a whole genome sequencing data set. And each of these gray bars represents a sequencing read. And what you can see here are polymorphic sites. This is, I believe, a GA polymorphism. And this is a CT polymorphism. And great resolution on that. I'm very confident in what those genotypes are that we're seeing there. Everything else agrees nicely with the genome. That's good. What we see in this lower panel is the results of so-called skim sequencing or low-pass sequencing for one of the CTLR animals. And what we see here is this animal has a variant at this position. We would refer to a variant that's found in an animal as either heterozygous or homozygous. Heterozygous meaning that they have two different copies. That is, they inherited a different copy from the dam than they inherited from the sire. In this case, it's very easy to tell that this position is heterozygous. For this position, it's a little more difficult just looking at this. However, with enough data across this region, there's a statistical test or statistical method that can be used called imputation. It's well-founded science, and it's something that can be explained just beyond the scope of what we're talking about here and now. But I'll be happy to come back and talk y'all through that. But with that, what you can do, so you can see you've got vastly more sequence data, all these pretty colors up here telling you what this animal looks like across this region, and much less sequence data in the $75 test. But again, the information that is encoded here is sufficient for the imputation process to derive genotypes entirely across this region, even where it doesn't have the sequence data. So what we did with the phase 1 grant was demonstrate that the genotypes that are predicted by the imputation process for the low-pass sequencing agrees with the results that could have been derived, or that would have been derived, from the whole genome sequence data for the same animals that we did the skim sequencing. And that worked remarkably well. And here are the results of that in table form. But what you see on the left here in table A are the genotypes derived from low-pass sequencing compared to the genotypes derived from the whole genome sequencing of the same animal. And what we have is in excess of 99% concordance across the genome at typically what is around 1.3 million positions in the genome. If you pick some other animal at random, the whole genome sequence data of some other animal just that was in the population randomly, and compare the low-pass sequencing data to that, you see that you get, on the between 5 and 10% disagreement with the genotypes that are called. So so what we've demonstrated here is that in fact the skim sequencing data is really very accurate, and it has the power to discriminate one animal from another, which is what we need in order to do these parentage tests and all the other genetic analyses that we hope to do. Okay, so what can we do with these genetic data? 3 tests that are pretty straightforward for us that we are happy to do with the data that you have. Parentage or meat identification. What is meat identification? Well, if you have you send a steer off for slaughter, you think that what comes back to you is not what you sent. If you take a sample from that animal and we have data, if we have genetic data existing in our database for that animal or for one of that animal's parents, either the sire or the dam, we can see if the genotypes from that meat sample are consistent with the genetic data that we have on either that animal or its sire or dam, and be able to report that to you. Parentage, we can confirm, or we can not confirm parents that are suggested when the test is submitted. We can do a genetic background test. That is, what do the genetics of your animal look like relative to all other CTLR animals in the book? And we can even assist with sire selection to choose a sire that might produce a calf that is more consistent with the genetic background that you're hoping to, that CTLR is hoping to achieve. Okay, parentage with SkimSeq. How does this work? Okay, so this is all just Mendelian genetics, but essentially in an actual sire, dam, calf trio, you could legitimately see something like this, where a sire is homozygous for the C, the dam is homozygous for the T, the calf would be heterozygous, CT, right? The only allele that the sire can pass is a C, the only allele that the dam can pass is a T, so the calf must be CT. Okay, we do that at 1.3. We ask this question: do we have a consistent pattern of inheritance over 1.3 million sites? And we get a lot of very good information, and we get a lot of information that that is what we call excluding if an animal is not in fact a parent, right? So another acceptable scenario, the sire is CT, the dam is TT. If the calf is TT, then that is something that could happen. If the sire is CC, the dam is TT, and the calf is TT, that is impossible. So this dam has got to pass a C to the calf. And if there's no C in the calf genotype, we know that this is a Mendelian impossibility. So it would be counted as an exclusion. Another such exclusion would be this one, where both parents are homozygous for the T allele and the calf is heterozygous CT, right? That C has to come from somewhere. Neither of these animals could provide it. As such, it's an exclusion. We can do parentage testing with one parent if you have a dam and a calf, a dam that's homozygous T, a calf that's heterozygous. That can work. If you've got a dam that's heterozygous and a calf that's homozygous, where one of those alleles matches one of the alleles that she has, that can work too. What can't work are opposing homozygotes, where you have a dam that's CC and a calf that is TT, right? Again, she has to be able to pass that C on to her calf. And what we will do, again, is we will look at all 1.3 million of these sites that have genotypes in all parents, the parents and the calf, and we will ask if the pattern of Mendelian inheritance is correctly obeyed, either this or if it's violated, something similar to what you would see in these exclusions. And we tally those. And what we get is going to be something that looks like this. So we had, I believe, about 10 trios, and with suggested parents, and we tested all of them. And what we found was that 9 of them had about 0.2% exclusions. Now, you are going, since we are not doing the whole genome sequencing, we're doing imputation, there are errors that are going to be inherent in that process, and they happen at about 0.2%. So that's not inconsistent with what we would expect to see. We did see one in one of the trios that we had, exclusions that were much higher than we would have expected, and this is almost certainly the result of misattributed paternity. In fact, we tested the dam and the calf by themselves, and she clustered. Those results clustered down here. We tested the calf with the proposed sire, and its number was way up here. Now, if you take a calf and you just pick 2 parents from the population that you all had provided me and pick them at random, and then do this parentage analysis, you get a distribution that looks like this. So I didn't screen for whether or not these animals were closely related. I mean, that is something that's going to happen, and could cloud a parentage test. But when I just chose, as I say, I just chose animals at random from among the ones that were provided. And when you do that, you see exclusion fractions that are somewhere between 2% and 5%. And they are on the order of 10% or tenfold greater than what would be measured in a correct assignment. So we do have a sufficient discriminating power that we can, in fact, corroborate parentage reports. Genetic background. Okay, what's all of this about? So we have all of this genetic data, and we want to ask the question, is a particular animal more genetically similar to this group of CTLR longhorns that are regarded as the ideal herd. And what we can do is we can genotype a whole bunch of animals. Here we have 10 on Ankylosing. We've got 4 CTLR cattle that are regarded as good, and we had 4 additional animals that have been sequenced by the U.S. Longhorns that have been sequenced by the USDA that were considered wronghorns. So we did what's referred to as a principal component analysis. So what does this do? This looks at all 1.3 million genotypes, and it asks the question, is there a group of these genotypes that can be weighted in such a way as to identify the greatest variance in this population? So there will be a large number of these principal components that are created, but the 2 that capture the greatest variance are typically named principal component 1 and principal component 2, or PC1, PC2. And essentially what this allows you to do is to take all of the genotypes and with these 2 principal components, derive a Cartesian point that can be compared to points derived using the genotype data for all the other animals that you're looking at. And what we see here is that the CTLR animals, the good ones, cluster nicely. The USDA wronghorns cluster nicely, and the Ankylosing are way the heck over here. Now, these data were derived using whole genome sequence data, so all of the genetic data that was available. And the question that worried us a bit, and that we were a bit anxious about answering was, would there be enough discriminating variation in the skim sequencing test to be able to do this, seeing as that test was not trained at all on Longhorns, and it certainly wasn't trained on Ankylosing. It was, however, trained on other very popular breeds such as Angus, Hereford, Holstein. So we had some hope that it would give us sufficient discrimination. So if you blow up the region that were just the CTLR and the USDA wronghorns, you can see that there's a clear separation along these 2 principal components. Now, when we used only the skim sequencing data, this is what we saw. Still pretty good separation. These 4 points here were the USDA wronghorns. The points over here are from the Ankylosing, and the points in this circle are the CTLR longhorn. So what can we say about this? Well, it looks like the animals who have the phenotypes that you all regard as most important, genetically, they seem to cluster together pretty nicely. And what this also says to me is that we can use that low-pass sequencing data set generated from any animal to see just where they sit relative to the rest of the animals that you have looked at. Okay, so how can we use these data to choose sires? Well, what we did was we took these are 5 trios, a sire, a dam, and a calf, and we looked at where they sat on this principal component table. So this is greatly expanded. But what you'll see here is that we have a sire, a dam, and the calf that they produced is somewhere in the middle. And similarly, so all of these shapes are consistent. So this is the this is the sire, this is the dam, this is the calf. Dam, sire, calf. This is the sire, the dam, the calf, the dam, the sire, the calf. And what's reassuring about this is that the calf is always between the sire and the dam. Not, obviously, if you've drawn a line between the sire and the dam, you realize that the calf is not on that line. But what we do see is that the calf does move toward a point that is between the sire and the dam. So let's imagine that this circle represents the genetic background that you all have identified as favorable for your Texas Longhorn. And this is a dam who's outside the circle, and you've got these four bulls that are comfortably inside the circle. So what would you which of these sires would you choose in order to produce a calf that would be that would have a background consistent with what CTLR is looking for? Well, you'd likely pick that one. And what would happen is it would likely produce a calf that might be somewhere there. And then this calf grows up to be a cow, and you want to take her and breed her to another bull. Which one are you going to choose? Well, if you want to move the progeny closer to the center of that circle, you're likely going to pick this one. Again, it looks like any of these other bulls would be suitable, and if any of them had a phenotype that you preferred over the other ones, then that would likely be the one that you would choose. But just for the purpose of producing a calf that would be moved closer to the center, you'd probably choose the one that's furthest away within the circle, and you would produce a calf that might be there. Okay, so all of those points that were on those graphs that I showed you, they are in this shaded oval here. So just to be clear that they weren't any of these other animals that were way the heck away and that you're trying to move a great distance. They were all animals that were safely within the background that you prefer. Okay, now some other quantity that you probably want to keep an eye on is something called heterozygosity. Right, so we have breeds. How do we make breeds? Well, we make breeds through inbreeding, right? We increase and fix the genetic components that produce the traits that the breeders want. And this is a good thing. So when I say fix, I mean every animal in, so, if we looked at all of your Longhorns, we would likely see an enrichment in certain genetic components that make Longhorn. And this is a good thing. When it becomes problematic is when you begin increasing the frequency of polymorphism, or the frequency of polymorphisms that produce bad traits, right? So you might have something that's kind of close, that's on a chromosome that's kind of close to one of the genetic element that produces the good trait that you want. So it might be coming along for the ride. Or otherwise it's just, hanging out there and just and by accident you've increased the frequency of this bad thing, and then you start seeing bad traits in your calves, and you're wondering why. Could be genetic. So a way to protect yourself against this is to monitor heterozygosity. So with this genetic test that we have, it is very straightforward for us to calculate the amount of heterozygosity that any one animal has. Further, we can identify, so, imagine there are 8 bulls that have traits that you would that you would very much like to see passed on to one of your calves, and you'd be happy breeding your cows against any of those sires. If you want to ensure the greatest probability of the greatest genetic diversity, beyond, of course, selecting for those traits that you want, what we can do is we can predict a distribution of heterozygotes that you are likely to see in your calf. Now, to be very clear, we are rolling dice here, right? So when you compare, I forget what dam we used here, but when we compared her to these 10 sires, Pepe Le Bleu would have produced a calf, if they produced infinite calves, right? The distribution of heterozygosity in those calves would look something like this, with a peak right about here. But they're probably only going to produce one, right? So where's it going to be? Well, most likely it's going to be in this range, right? Right around the peak of the distribution. But there's a non-zero chance that it's all the way over here. And likewise, if you pick Dublin-Dixie Yates, which is most likely to give you the least genetic diversity, you could produce a calf that's got heterozygosity all the way over here. It's really unlikely, but it could happen. What is absolutely true is that it is most likely that Dixie Dublin Yates would produce the least genetic diversity, and Pepe Le Bleu would produce a calf with the most. With the data that we have on your calves, with the data, if we have these data for the bulls as well, this is an analysis that we can run, and this is a prediction that we can make for you. Okay, so where are we with respect to a full system capable of ordering? So our SBIR phase 1 grant, it helped us to build what is referred to in the business as an MVP, a minimally viable product for ordering and data management. What does this mean? Well, it means that we currently take orders manually. We've built a database, we've built some software that kind of sort of looks nice, but it doesn't do much. All of the analyses that we've built, that's all code that's been written and that's been tested and that works. And that is all code that we are able to manually run to analyze your data. So data coming in at the rate that is coming in now, tens of animals over a couple of months, we can easily handle doing those analyses manually. We can generate and analyze these data manually, and we're doing all of this in the crowd. But what we need to work on right now with you all is a set of rules. And we need to look at the data that we have generated, and we need to establish what are thresholds for the fraction of exclusions that you will accept in a parentage test. We need to establish just what that region is going to look like, and by that I mean just the Cartesian definition of it on the principal component graph for your genetic background. We need to establish what that's going to look like in order to identify an animal as being consistent with the genetic background that CTLR wants, or inconsistent. And with respect to a full system, our SBIR phase 2 grant, which was for a great deal more money, we can actually produce the production system. And we will be able to take orders via this system. We're setting up to take credit cards right now, and we'll be able to generate and analyze the data automatically, and create your reports automatically, so that we can send those to you. What I want to convey to you is that the hard part of what we were trying to do has been done. We've demonstrated that this skim sequencing test can work to do the genetic tests that I believe you all are interested in doing. And what we need to do now is software development. And I've identified a team of software developers, and we are going to be working to build the online system to make this function the way that it needs to for you. And one thing that I want to be very clear about is these data do belong to you. And by that I mean, the data that we are analyzing, right? If I gave you these raw files, they're probably not going to mean terribly much to you, but there are other people and other groups out there that would be capable of analyzing these. And I am very happy to share these with you if you believe that you can get value out of them, even if it's beyond working with us. And with that, I will close. My email address is ted@Invictus Informatics. Debbie knows how to get in touch with me, and she and I have spoken and corresponded often. Um, Whatever questions you have, I will be pleased to answer as best I can. And if there is more time that you would like me to spend with you all to work out what these details are with respect to thresholds for parentage and for genetic background, that too is something that I'm very excited to begin on. So thank you very much, and I look forward to working with you all again.